Good afternoon and welcome to Nordic Ventilation Forum. This is the third time we organize this forum, hopefully not the last. The topic is most interesting and topical. Can air cleaning replace ventilation? Now we have today several interesting presentations dealing with this topic. This forum is organized not only by us, but together with the Nordic building authorities from Denmark, Finland, Sweden, Norway, and Iceland. And this forum is recorded, and the presentation, which we will see soon, will be available later this week in the Scanvac website later this week. And you can also ask or comment that presentations through your question and answers chat, and the speakers can answer directly or publicly after the speech. But now we go to the topic itself. Let me introduce first myself. I'm Professor Emeritus from Helsinki University of Technology. After that, after retirement, working like RIVA Secretary General and various international organizations. But it's my pleasure now to introduce Hans-Olof Karlsson from Swedish Building Authorities Boverket. He is the main or Chief Executive Officer dealing with sustainable buildings, indoor climate and energy issues. We are pleased to have you here, and he's also the chair of this Nordic Authorities Ventilation Authorities Group. Please, Hans-Olof, the floor is yours.
Thank you, and I also say welcome to this forum that we started some years ago, and we found out that it is a very good help to when we're coordinating our authority work to have a group working across the Nordic countries to see what's on in the Nordic countries. And we're also happy to have the Nordic Ventilation Group with researchers and representatives from the industry of the different countries that are welcome to this forum. And as Olli said, there is a lot of interesting parts of the today's program. So I think I shouldn't take too much time. So I leave the floor to you again, Olli, to start presenting the main speakers here and what they are going to speak about. Thank you.
Well, thank you, Hans-Olof, and thank you for your contribution for this group. And hopefully, as you said, this group can work together in future and produce some common practice in Nordic countries. Thank you. But the topics of today cover both literature reviews, experimental, and many other work. The first speaker is Siru Lankvist. He's executive director of Scanvac, Finvac, and many other organizations. So pleased to have him. And she will, in her speech, kind of discuss and review the Nordic ventilation requirements, which is very interesting to see the similarities and differences. The next speaker, we are pleased to have Professor Ali Ashari from Aalborg University. And he has made an excellent review of literature dealing with the effects of air cleaning on air quality and health. That's the most interesting summary. And the third speaker during this first session of the webinar is kind of case study. Senior researcher Hanna Leppänen from Finnish Institute for Health and Welfare will describe the study or experiment and results how the air cleanness had an effect on exposure, air quality and human responses. That's the most interesting study. I don't use more time to go to the backgrounds of the speakers, but please note that we have at the website a kind of a nice summary of the CVs of these distinguished speakers. Please visit the website again and enjoy the background of the speakers. But let's go further and start the seminar with Siru Rönnqvist's presentation on requirements for ventilation and air cleaning in Nordic regulations. Please, Siru.
Thank you very much, Olli. Let's see if I get the right slides here as well. I will shortly tell you about the requirements for ventilation and air cleaning in Nordic regulations. And this material is part of a cooperation that we have had ongoing for a couple of years now. We have cooperation among authorities, among the academic, in the Nordic Ventilation Group, and also the industry cooperation has been intensified. And this comparison has been made by the authorities. And why we do cooperate is quite natural, because here in the Nordic countries we have quite a similar climate, similar culture, and also our building constructions are quite alike. So it's very natural to have cooperation. And what kind of cooperation do we have? Mostly sharing of information and comparing information. And also this comparison is part of this information sharing. Well, if we start with some overall observations about the regulations in the Nordic countries, the structure of the regulations and guidelines is a bit different between the countries. There are also several different national authorities that give regulations for the same parameters. In this comparison, we have mainly looked at the regulations from the building authorities. In some countries, you refer to standards, and in others, you don't at all. And it's not the same parameters that are regulated in all countries. And there is also a large variation how the parameters, if they are regulated as mandatory or on a guideline level that's not mandatory. So let's dive into the deep end and look at some numeric values. First of all, we looked at the minimum ventilation rate per person. In Denmark, there is no numeric value for the ventilation rate, but there is, however, for schools and childcare facilities, some regulations that say that it depends on the CO2 level that has to be designed under 1000 ppm. In Finland, we have regulations that say that we have to have a minimum ventilation rate of 6 liters per second per person. In Norway, in residential buildings, in the bedroom, there has to be at least 26 cubic meter per hour per person when they are in use. And that's compares with 7.2 liters per second per person. And the same requirement for public and commercial buildings as well when they are in use. In Sweden, there is no quantity requirements in the building regulations, but the intended use has to be considered. There is, as I mentioned, however, other authorities that can give some regulations. And for example, in Sweden, there is some regulations from the occupational health side for the ventilation rates. When we look at the whole building and the ventilation rate per floor area, in Denmark, in childcare and teaching facilities, you have to have 0.35 liters per second per floor area when there is no occupants, and in residential buildings, 0.30 liter per second per square meter floor area when they are in use. In Finland, we have 0.35 liter per second per square meter, and then you have also to consider the intended use. In Norway, residential buildings 1.2 cubic meter per hour per square meter, and for public and working place buildings 2.5 cubic meter per hour per square meter. And both these values when these buildings are in use. In Sweden, there is 0.35 liters per second per square meter, and also the intended use has to be considered. If we look at apartments, in Finland we have a requirement of 18 liters per second per apartment, and in Denmark there is not a requirement per apartment, but per the square meter of heated floor area when the apartment is in use. In Norway as well, 1.2 cubic meter per hour per square meter when they are in use, and in Sweden there is no quantity requirements, but you have to consider the intended use. When we look at control of ventilation rate by demand, and specifically in residential buildings, in Denmark they say if there is no occupants and there is no demand for ventilation, the ventilation rates may be reduced to 1.15 liters per second per square meter. In Finland, you have to have a possibility to increase the ventilation rate with 30% and decrease it down by 60%. In Norway, it's allowed to reduce it down to 0.7 cubic meter per second per square meter in rooms that are not in use all the time. And in Sweden, there is no quantity requirements, but they say that it's possible to increase or open windows or shutters. And the CO2 level. For Denmark, as I mentioned, in childcare facilities and rooms for teaching in schools, there is a requirement that you have to stay under 1000 ppm in design conditions. In Finland, it's 800 ppm above the outdoor CO2 level. In Norway, no quantity requirements, but they say that the ventilation must be adapted to the pollution load from people. And in Sweden, there is no quantity requirements, but the intended use is to be considered. Then we look at the air filtration and air cleaning. In Denmark, nothing about this in the building regulations. In Finland, we don't have any numeric requirements, but the level of air filtration must be designed based on the quality of outdoor air and the indoor air quality target set. In Norway, there is no requirements in TEC 17, but there is some instructions given that support TEC 17. And in Sweden, there is no quantity requirements, and they advise to a standard. The use of return air, the air circulation. In Denmark, no requirements, but all the air volumes that have been mentioned here before, they are all to primary air, not recirculated air. In Finland, you're not allowed to have any recirculation of exhaust air from categories 2, 3, and 4 at all. And in Norway, no recirculation if it contaminates rooms where there are people present. You can, however, use recirculated air as part of the ventilation in rooms that there are no people, and it doesn't cause any unwanted spread of pollution. And then they also said that the recirculation must be filtered. And in Sweden, they say that recirculation is allowed in public buildings if the indoor air quality is guaranteed. And it's okay in dwellings within the same apartment. And also here if the indoor air quality is guaranteed. Then we looked if there is something said about rooms where you can't have any air circulation. So no air circulation in Finland in residential buildings, commercial kitchens, hotel rooms, classrooms, daycare centers, hospital wards, restaurants, and other rooms that have some specific requirements of air quality. In Norway, they say that rooms with poor air quality, like copy rooms, toilets, kitchens, must have negative pressure in relation to surrounding rooms. And garage and rooms with polluting industrial activities must be technically separated rooms. In Sweden, no recirculation is allowed from bathroom, kitchen, and similar room types. That was very shortly some comparison about the requirements. Overall, we can say that functional requirements are more widely used today. So there is less number values, and it seems like Sweden is in the one end with very little numeric values, and in Finland we have some very specific values. But in this new world with digitalization, we would need more also number values. So we have a bit of a conflict here. Thank you.
Thank you, Siru. May I ask a question? Can you hear me? In the beginning, you mentioned that the standards are not used very widely. However, we know that there are many standards on European level which are used in some countries, but are they used also in Scandinavian countries or not? And if not, why?
Yes, they are not that widely used. For example, here in Finland, you are not allowed to refer to a standard that you have to pay for. So all the requirements has to be in the law, and other requirements that are free for everyone here in Finland. In some countries, you refer to some parts of them, but it not very widely.
Okay. What do you think? Should they be used more?
Well, that would harmonize things. So in that way, yes, but as I said, there can be some problems using them when people have to pay for them.
Sure. Okay. What about you mentioned some of the control or the ventilation rates. Is there any trend that there's more requirements? I saw that in Finland there's some specific requirements for ventilation rate control in residential buildings, but any requirements in other type of buildings in other countries?
Well, at least you get the requirements from the part that our buildings has to be more and more energy efficient, and the ventilation uses a lot of energy. So we have to use the ventilation wisely. So demand control ventilation is needed if you want to have very energy efficient buildings.
That's certainly true. But what is there any trend or thinking on Scandinavian level on the topic of today's seminar with the future? Can the ventilation rates be reduced or keep the same even if the air cleaning is improved?
Well, it seems that you can't replace ventilation with air cleaning. That's not a solution. That I think that has been quite clear in all the discussions. And there is discussions ongoing if we should increase ventilation, for example, in pandemic situations. But we don't have exact information at the moment. But there is a discussion ongoing how the ventilation should be designed in the future.
Okay, that's certainly a very important topic, and fortunately, in the end of the seminar of this webinar, we have the presentations dealing more in detail this topic, and we are looking forward to next speakers. And thank you, Siri, for this nice summary of the Nordic ventilation standards. Thank you.
Thank
and
you.
We'll go further to the next speaker, who is Hanna Leppänen. No, it's not Hanna. Sorry. It's Professor Ali.
We have a little problem here because we have some troubles with Ali connecting. So if it's okay, we go take Hanna.
Okay. Is it okay for you? Oh, sure.
Yeah.
It looks like it. Okay. She is a senior researcher from Finnish National Institute of Health and Welfare, and will describe an interesting study, fifth case study on the effect of air cleaning on air quality, exposure, and human responses. Please, Hanna.
Thank you very much for the kind invitation. And first, I want to express my sincere and deepest thanks for Professor Emeritus Olli Seppänen for the kind invitation to talk in this webinar. As a student in the university, I was already admiring your job and still do. I was studying your book called Air Conditioning Technology and Indoor Climate. And of course, back then, I couldn't have dreamed to be in this position and studying the same theme. But the motivation for this study was that I was 10 years ago making also our national literature review about air cleaning techniques, how they affect on the exposure and also on health. And I could see back then that many of the studies are done in controlled chamber or test rooms. And of course, those situations are very different from the real world, for example, in schools. And the results from the chamber studies cannot be straightly extrapolated to the real world environments. And this is why we need also studies in the real environments where there are lots of different sources for the pollutions. They are differing, there are people changing, the amount of people, what they are doing, different activities, there are some sources, and also the ventilation and the airflows are differing in classrooms. So that was the motivation for our study. The study is called PUHO, which reminds me of breathing. And the objective of this PUHO study was to perform a comprehensive assessment of effect of air cleaners on different indoor air impurities. So we assessed particulate matter, also volatile organic compounds, as well as indoor microbes. And this was tested in occupied Finnish classrooms. We wanted also to see how the air cleaners are affecting on the pupils' perceived health. And the real aim was to provide this real-world research data on the efficiency of air cleaners, as well as the effect on perceived health. Here in this slide, on the right hand, you can see a very typical classroom in Finland. You can see how the exhaust air and supply air are placed in that room, and windows are typically on the other side of the classroom. In the study, we put always 2 air cleaners with the same model in one study classroom. And here you can see the typical positioning of the air cleaners and the measurements. This study was done during one school year, and as you might know, in Finland and in the other Nordic countries, we have many seasons in one school year, so they were also included in this study. We had altogether 18 classrooms, which were located in 6 elementary schools in southern Finland. And these 2 air cleaner units were the same type, same technique in one classroom with moderate airflow. Here is the illustration of the study design. The study always started in every classroom with a baseline period where there were no air cleaners still used. And we wanted to see what is the normal exposure and how you perceive your health in the normal situation. After that, we had 2 phases. So normal air cleaner operation with this green box, air cleaner on, and then the air cleaner sham operation, where the air cleaners didn't have the filters, it only recirculated the air. And these 2 latter interventions were conducted in the blinded and mixed setup. So half of the classroom started with the normal operation and the other half with sham operation, and then they were changed. As I said, we had different kinds of air cleaning techniques. So we had techniques, HEPA filters, activated carbon filters, and also in one model there were electrostatical precipitator used. The amount of activated carbon was differing between these different models. And as I said, the sham operation was always done so that the filters were taken away from the air cleaners and it was only recirculating the air. Then on methods. As I said, we did lots of measuring of different indoor impurities, and for particulate matter, we evaluated the variation of PM10 and PM2.5 levels during these 3 study phases by continuously measuring with optic small device. We also got the outdoor data on particle levels produced by Helsinki Region Environmental Services Authority, and we used that data to normalization of the indoor particle levels. And for chemical impurities, we measured volatile organic compounds once a week during 90 minutes of school day measurement. And it was done with 10x adsorption tubes in every classroom of the study, and also to see the outdoor exposure from the schoolyard. We collected settled dust samples to see the microbial exposure in those classrooms by passively collecting the dust onto the Petri dishes. we put the Petri dishes up on shelves in the classrooms out of reach from pupils and also away from major airflows. And also we took active air sampling with the button aerosol samplers, and this was done with a period of 5 days during school hours in every study phase. From these two sample types, we did quantitative PCR analysis to see the different microbial groups and their levels in the study classrooms. In addition, we had the symptom diary for the pupils, and it was categorized for different symptoms, so for lower and upper respiratory symptoms, and then more general symptoms. And pupils filled this diary daily. The teacher was assisting them, and this was done throughout the 3 study periods. And then we can move to the interesting part, so to the results. Here are the results of particulate matter, and you can see here in the figure, the blue box is the air cleaner normal operation and the red is the sham operation. And if you compare the operation with filter, the mean difference between measured and expected PM2.5 levels were 28% less when comparing to the baseline. And for sham operation, it was less, it was 6%. Then on PM10 levels, it was about the same when operating with filter, so 29% comparing to the baseline. And for sham, there was nothing to be seen comparing to the baseline. These changes were not statistically significant. Then on volatile organic compounds, and it has to be mentioned that these levels in the study classrooms for VOCs were really low, which is typical in Finland. And as a matter of fact, they were much below our national guideline limits. And when the filters were operating, the air cleaners were operating normally, a decrease of 25% of total volatile organic compounds levels was observed when comparing to the baseline. This was not statistically significant, and with some operation, it was opposite, so a tiny increasement was observed. Here are the results from the UPCR measurements. And here you can see different microbial groups. So Cladosporium herbarum, this herb, this is representing outdoor fungi. And then this PEN-ASP, Penicillium aspergillus B variety group, is targeting of the most prevalent indoor fungal species. Then there is gram-positive and gram-negative bacteria, and this Unifung is for total fungi exposure. And with the filter operation, we found a non-significant decrease from 22 to 71% in levels of these different microbial groups. And this was for air samples. And also the sham operation was decreasing the levels similarly or even more comparing to the baseline. But then when we go for settled dust sampling, the result was a little bit different because the differences between the air cleaner operation status were inconsistent and statistically non-significant between these different microbial groups. Here are the results for the symptom reporting of the kids. So in this figure, there are these 3 different categories. So lower respiratory symptoms, upper respiratory symptoms, and these more general symptoms. And in these bars, there is the variation between these different study phases. And from this first part, lower respiratory symptoms, we can see that the filtration of air cleaners reduced 4% of the symptom reporting. And for upper respiratory symptoms, it was 5%. And for more general symptoms, it was also 5% decrease. And these were all or almost statistically significant results. But the interesting part is that when you compare the normal operation to the sham operation, there is no differences between the reporting of the symptoms on those phases. We got altogether 294 symptom diaries from the kids, but we wanted to select those that have reported 50% of the study days, so we could see more statistical power in the analysis. Then on conclusions. So this study showed no significant impact of air cleaner operation with the used clean air delivery rate, what we had in this study for the air cleaners. But we could see moderate reduction for these different indoor impurities, both sham and normal operation of the air cleaners. And this finding that both sham operation and filtration decreased the symptom reporting from the pupils, that actually needs to be studied more. We have to take into account the placebo effect behind of this, because the pupils didn't know when the air cleaner was operating normally and when it was only recirculating the air. And they were both cases experiencing less symptoms than normally. However, in this study, we also observed reduction of some particle and microbial levels with the sham operation. And of course, that can be also the reason behind of this. And that's why we need more studies on this, and with bigger ends, more schools, more classrooms, more pupils to be studied. And in Finland, the levels of indoor air impurities are really low, normally in schools. If they face problems, they are moved away to a new good building. And this is why normally in our studies, we don't see the situation with bad indoor air quality, really. And in Finland, the ventilation is normally good. Of course, there are some older buildings that are lack of ventilation, but normally it's very good. And then the situation is so that the air cleaner is not helping that much above the normal ventilation. But thank you very much for your attention, and I would like to thank our study team, which is named here. Thank you very much.
So, thank you, Anna. Thank you very much. Very interesting study. I have a question related to CAD airflow rate through the filter. You said that it was from 200 to 400 liters per second. How can that compare to ventilation rate? Was it the airflow bigger or lower? Which may affect on the results.
Yeah. Thank you very much. That is a really good question. Actually, we've made a follow-up study after this in another city, and we measured the normal ventilation in those classrooms, and actually it was the median was 774 cubic meters per hour. So the air cleaner is much less the airflow there than the normal ventilation. And of course, if we think RIHVA's recommendations, it should be more. But this is the typical airflows that are used in air cleaners when the companies are selling those to the municipalities.
So what does it mean? Is it too low or?
I think it's too low. If you want to really see the effect and reduce the exposure, it should be more. But then it's about the noise also, because people see they are too loud. So you should have more of them with a lower airflow. So it's problematic. But I would think that we should also study this in real environments in other countries, maybe some more exposure, and see there what is the limit that you can see statistically significant reduction.
One thing was very surprising also in your results, that you to a certain extent got the same result in sham operation and real operation. Is there any way to explain that? It sounds a little strange.
Yeah, actually, when you see the exposure, it was a little bit less, which is a good thing for the companies. But if you see the reporting, symptom reporting, it could be the placebo effect, because when we brought these air cleaners in the study classrooms and they were not yet operating, already then the people were thanking us that this is really effective, even if it wasn't plugged in. So there is this psychological effect also that has to be taken into account.
Okay. What about the location of the air cleaners? They were the same. You didn't change them during the study?
Yeah, they were always the same, and 2 air cleaners were put in opposite position, and it was same throughout the study.
Any opinion? How should was that the optimal location, or is there a reason to study that more carefully in the future to get the optimal location?
Yeah, actually it could be, and also some modeling could be really nice with this.
You didn't do any modeling, no?
No, it was only based on the companies that were telling us how to do it.
But the plan is to continue the study, understood?
Yeah, and actually we now are reporting of the follow-up study, so hopefully to present those results soon.
Maybe in the next forum, Nordic Ventilation Forum, we get
let's keep it in mind.
Okay, thank you, Hanna, for an interesting study and results. Well reported. Thank you. And then we go in the program further, and now we have Professor Ali Ashari from Aalborg University. And as I said, he has made an excellent summary of studies on air cleaners and human health, or literature review. Please, Ali, please share the information with us.
Thank you very much. Oli, do you hear me?
Yes.
Yes, thank you very much. And I'm going to talk about air cleaners and human health. This study is based on several articles that we reviewed in NVG. And I'll start with a very brief background that air cleaner, also known as a air purifier, have long been used to improve indoor air quality by removing pollutants such as dust, pollen, and pet dander, smoke, mold, spores, and even certain gaseous contaminants. And in addition to this one, several health issues are associated with poor indoor quality. Respiratory conditions such as asthma, allergy can be started or intensified by airborne particles. Additionally, some studies suggest a link between the long-term exposure to certain indoor air pollutants and more serious health conditions. Actually, the main purpose of air cleaner is to filter and purify the air, reducing the concentration of these pollutants. They can be particularly beneficial for people with respiratory conditions, elderly, children, and those living in an area with a high level of outdoor pollution. Multiple study have investigated the ability of air cleaner must find that these devices can significantly reduce the level of certain pollutant in indoor environment. So the idea was, so we can look at these studies and go in deep and see, we can see if we can change. Okay. Yeah. So in this study, we make a comprehensive review of the article in this area. And the idea behind that is to find relationship between the air purification and human health. The methodology that we use for this review is we look at the keywords and air purification, HEPA filter, indoor quality, respiratory health, allergy, and a lot of keywords we use it in order to show, to find the materials. And after the material was found, so we went to the categories of the articles. We divided in asthma, cardiovascular, nasal, high fever, and other allergies, adverse effect, mixed, and general. So total 97 article was found and 60 article was reviewed. But the review of article on the progress now, and we are not in the end of analysis. We are going to analyze this until next year. The idea is that in the maybe April or something like that, we are going to publish this result. I'm going to use some words here, talk about portable air cleaner and air purifier, the filter used in the study, but the type of technology is not specified when we say portable air cleaner. When it is air filter, portable air filter, air cleaner, HEPA filter, names are used based on the technology identified in the articles. A specific health, when we call it for a specific health, it means the conclusion of the study specified the impact of the air cleaner on the specific sickness in an indirect way. It means that they measure other things and try to show that one sickness become better. General health, when we say general health, the overall effectiveness of the air cleaner on the specific sickness and human health was shown when we say general health. And special cases, in the special cases along with the portable air cleaner, the changes were made in a ventilation system of the building to improve sickness or human health. That was the word that I used in my presentation, and I try to define what I mean. If we look at the different categories, asthma, it was actually people between age 5 and 16, male and female, and 8 articles was in this area, and in 5 study was a HEPA filter was used, and the rest of the study the rest of the study were conducted under air filtration and PM 2.5 filtration. 4 articles were studied on the specific health and 4 on the general health. Cardiovascular, that was people between 19 and 75 years. 9 studies was started, were conducted on non-smokers and no related cardiovascular disease, and it was couples maybe and adults and young and healthy male or female. 7 of them use HEPA filter, 1 was mechanical filter, and 2 was portable filtration. And 5 articles focus on the health part and the general health. 2 were special cases and 2 were literature review. About the high fever, it was 1 study was conducted with the 44 other male and female volunteers, and 2nd study was conducted in a fresh air filtration bedrooms. So we could find 1 study as a hole in this study, and he used a HEPA filter, and one laminar flow HEPA filtration technique was used. One article was a special case and general health, and the other was a specific health. Regarding the nasal and respiratory, so it was people between 4 and 90 years. 8 studies were conducted. 2 were on home, 1 was on a dummy, and the rest were on children. 4 HEPA filter, and 4 of the study had a HEPA filter, and 2 other air cleaner were used. And one of this article was a special case, and 3 was as a health, and other was a specific health. And regarding the adverse effect, so it was people between 5 and 60 years. 12 studies were conducted on children with asthma or residents with smokers in classroom, and on patient and health colleague study, and on animals. So 4 was air filter, 1 was air purifier, and 1 was portable air cleaner, and 1 was electrostatic, and 1 was carbon and HEPA filter. Regarding the health, 1 article was a specific case, 5 was general health, and 4 was health, specific health, and the other was literature review. We look at the other allergies, also was with people between 18 and 45 years. 2 studies were on a literature review, and 2 were on patient, and the other was on bathroom occupants. So 1 was in this study, one article used air cleaner, 2 was HEPA filter, and 1 was cold plasma air filtration and portable HEPA filters. So it was also article on a special health, and 2 was in a general health. And we look at also mixed study and also general study. So in mixed study, it was 2 articles, and in general study was 12 articles that we look at that. So I go through the sum of this finding that we have. Park and Emerich and Hong show different results here. I cannot read all of them. It takes a lot of times. But if we go a little bit more in detail, so we can see that for example, the study from Dang showed that the real purification using ionization air purification efficiency reduced particle matter and black carbon level by a significant percentage, while increasing negative air ion. It was associated with a 4.5% increase in the force exhaled volume in 1 second, and 14.7% decrease in fractional exhaled nitrogen oxide. So that's one of this article that was interesting to see that they have a number. The rest of the article, if you look at that, is much more look at the overall when they use the intervention with the air cleaning, so they can see the improvement of the health. Regarding the key finding regarding the asthma, also we have from the 3 of them, they look at the, for example, PM2.5 filtration devices, and they look at the they've tried to find what happened with the children with asthma and so on. But if we go in a detail, so we look at the one of the articles show when filter were used, average PM concentration was decreased by 69 to 80. So most of this study, so we look at that. They look at how much efficiency of air cleaner has an influence on a general health, that it can be better or it can be improvement in health or less improvement in health. But what we need here is in detail go and study what happened and what function in a health can be improved. So we need more evidence in detail than overall. But most of the study show also show only the evidence. One of the study, for example, from the QE talk about true filtration, result in a significant reduction in the total airway resistance, call it for around 24 of reduction, small airway resistance 43%, and resonant frequency 22%, and increase in airway resistance is 70%. So you see that one of the technology can influence in a, for example, airway. So such a study is important that we can see what happened in the body actually. We have also I have a problem here. Regarding the high fever, we have also here some study that funding strongly support the idea that the fresh air filtration system can provide high fever relief and improve respiratory health by reducing allergen exposure to the significant extent. But if we want to go in a detail, so we can see one of the study show among volunteers suffering only from the high fever, 83% of volunteers reported decrease in high fever after using air filters. And for volunteers suffering from the both high fever and perennial allergy symptoms, 69% reported decrease in both allergy symptom and high fever. And another study that Maurice was involved with does show that significant improvement in symptom scores with an average improvement of 26% in the morning and 24% in the evening. We have also looked at the allergies, and here we have a much more general impact of air cleaner in allergy. But if you go a little bit in detail, so we can see that utilizing both active air cleaner and mattress covers. So these are two things that you can see can be simultaneously used because the mattress can absorb a lot of these particles and gases, show a statistically significant improvement in airway hyper responsiveness by 20% fall in forced expiratory volume in 1 second. That's a one PC20 is that you can measure it during the one time, and that call it for PC20. Another study showed that the HEPA room filter in a 24-hour test removed 80 to 90% of the pollen and fungal spores and particles in a bathroom. As compared to 50% removal due to the sedimentation in a comparable control bathroom without a filter. We have also other studies, so we can continue a little bit more, so we have a time for discussion. Regarding the other, adverse effect in context of mite allergy patient with relatively low allergen exposure, HEPA filter air cleaner alone, say that the study was like that, there may not be sufficient substitute for standard avoidance measures. That was one of the important things that I think we have a little bit different study. And another study show that they show that it had no demonstrated impact of improving health when he studied the PM 2.5 concentration in a ordinary home. And the finding also aligned with the conclusion that air cleaner in this particular context did not lead to significant improvement in their respiratory health and health others. So we have a lot of study that we can go in detail and analyze it. So as a conclusion for this study, air cleaner actually, as my understanding now, is the air cleaner reduce indoor particle levels, benefiting individual with allergen and asthma, the lower allergen exposure leading to symptom relief and better quality of life, especially in older adult. Air cleaner help maintain vascular function and supporting heart health and reduce allergens, liable high fever symptom, promoting comfort, and air cleaner enhancing overall indoor air quality, contributing to better health. So as a conclusion, I will say that we have to be careful, draw conclusion here, because we have analyzed the result. But what I can see when we look at the overall health, we can see that it is fine. But when we look at in specific what function in the body improve, we have a lack of knowledge and we need to improve it. Thank you very much.
Thank you, Ali, for the nice summary, and we are all looking forward to receiving the final results of the study. But I've a couple of questions in my mind. You mentioned that in some studies there were some quantitative results as well, and I was wondering, can you say in which area those quantitative results are most reliable? I mean, that one study is not enough, but is there any specific area where there is a significant effect?
Actually, when they measure indirect health, it means like blood pressure or something in the pressure, and also viscosity of the blood. So they can show, for example, that has an effect on people. One of the study was, for example, the elderly people was exposed to particles, and another one was with the particles and no particles, and they show that viscosity in the blood change. So in this way, they can say they have a health effect, but much more in an allergy they can show in general that has an influence. But in detail, that you want to look at the DNA and also say on a airflow in a airway in your throat. So they have shown some result, but we need much more. It's difficult now to draw conclusion. We need more result.
Okay. Then still one important practical question: what should be the airflow rate be in fact CIDR be to be effective, to have any effect?
That's a very good question. That's a very nice question. I mean, when we talk about delivery rate, cleaner delivery rate, so actually, I mean, I don't know the limitation, how much should be in order to have a better indoor quality and also be energy efficient. That's a very good question that we need more data about that.
Yeah, I think that we recommended that it should be at least 2 air changes per hour to be effective.
Exactly.
And
but we need...
Yes, please.
Sorry. No, please.
In Hanna's study, previous study, it was, I think, range half of air change or 1 air change per hour. That may be the reason that she didn't find any significant effect.
You are totally right, and I agree with you, but we have a recommendation based on this study that we have today, but I think still we need a little bit more that we can see energy efficiency in this one and also health in this one. The problem is not energy efficiency, the problem is combination of health and energy efficiency together, so we can give a more accurate recommendation.
Yeah, exactly. Okay, so lot of work to be done.
Yes.
Good luck for your future studies. Thank you very much.
Thank you very much. Thank you.
And now it's time to have a break. We have a 10 minutes break and start again in 2 or 1 or depending which country you are in. See you soon again. Thanks for the speakers of the first session. Thank you and welcome back to the webinar. We have 2 speakers, distinguished speakers left in the second part, and first is Professor Bjarne Olesson from Technical University of Denmark, from International Institute of Environment and Energy, and he's speaking about the results of IEA Annex 78. Please, Bjarne.
So can I take control?
Yes, you can.
Okay. Let me see. Are you seeing my slides now?
No, not yet.
Okay. Let me see. But the one where I had to go to take control, I don't see that anymore.
Well, if you like to, I can share your slides.
Yes, I don't know why it's not coming up. Yes, you can bring up my slides.
Excellent.
Okay. So we have an IEA annex which are led by Pavel Vagocha and myself, dealing with supplementing ventilation with gas phase air cleaning. Next. So this has been going on for some year. We are in the final year of the project, so you will see more results coming up during the next year. Next. One of the reasons what initiated this is that we have seen earlier in measurement of the performance of air cleaners using human perceived air quality. We have seen, for example, here a case where you have building materials as sources, and you see here at the left axis is the higher number, the worse people feel it. And with the blue, the air cleaner is not on, and with the yellow, the air cleaner is on. And you see here that the air cleaner works. People feel the air is better when the air cleaner is on. Next. Now we did the same where the source for the pollution were human bioeffluents. So now there were people as source. And what you see now, the orange is higher than the blue, which means when you turn on the purifier, people feel the air worse. And that's the problem we have seen. Some air cleaners, people feel the air is worse. Next. So in most standards today, when the deciding amount of required ventilation air is really based on perceived air quality, how people feel, or you can say the comfort of indoor air quality. And you need to know how many people are in there. and how much you ventilate per person, and then you add something for the emission from the building itself. So this is based on perceived air quality. Next. But if you look at the testing standard which exists today for gas phase air cleaners, and I should just emphasize, I'm talking about gas phase air cleaners, not filters or filtration of particles. So here the standards are made so that you challenge the air cleaner with a substance. It could be formaldehyde, it could be some other substance, and you measure before and after the air cleaner to get the efficiency, and then you can also get the corresponding clean air delivery rate. Next. But we say there is a need for new standards where you also measure perceived air quality and where you also use human being, the emission from humans, because we have people in all buildings and that's why we ventilate. There is a publication from AIVC where we have presented the concept for substituting ventilation by gas for air cleaner. So the idea is if you, for the air cleaner, can determine the equivalent clean air delivery rate, you could decrease the required ventilation with the same amount. Next. There are standards to measure perceived air quality. Is not new. That has been done in many industries. There's also ISO standards telling how to do it. Next. And we had just one standard now, which is focusing a test method for measuring perceived air quality for use in testing the performance of gas phase air cleaners. That's now out for the final vote, ending in November. Next. And what we are working on, based on some of the studies we have done in the annex, is then testing of gas phase air cleaners for improving perceived indoor air quality. It's done by the same ISO group which has done the other standards for testing gas phase air cleaners. We have decided at a recent meeting in September, we won't make a final standard, yes, but we will make what we call a technical specification, which is written like a standard, but it's a trial period of 3 years, so people can use it. Next. So this proposed technical specification is based on some testing we have done, especially at DTU, on different air cleaners. So the setup we had 3 identical spaces, but you could do it also with 1 space. So we could expose an air cleaner. We had a partition. The air cleaner was behind the partition. So people who went in to evaluate the air, they would not be able to see air cleaner. We could also have a pollution source from building materials in a box they could not see. And we could have people sitting behind this screen. So we also could have people alone, or most cases where we have a combination of people emissions and emissions from building materials. So either you can go in and have a whole body exposure, but you can also measure by taking out, extract air from the different rooms, and then people evaluate here outside. They don't see the room in a funnel. Next. So here you see the screen where we can, the air cleaner is behind also the people who simulating human bioeffluents. In this box we have an old carpet which we have used in many studies, emitting mainly VOCs. Next. You see here people, we can talk about whole body exposure. They go in and the first sniff, they evaluate the quality of the air on 2 scales, acceptable scales and odor intensity. Or you can do it by this funnel and basically do the same. Next. So we have the test we are proposing is a two-stage procedure. First, to test if the air cleaner improve the indoor air quality or doesn't have a negative effect. If it has a negative effect, there's no reason to do more studies and try to find the clean air delivery rate. If it passes the first, the stage 2 is that we try to determine the clean air delivery rate for this particular air cleaner. Here we use sensory assessment, like I've just described, by a human panel, around 30 persons. It depends on how accurate you want to make it, but normally around 30 persons. So we are not having any effect on long term. We are doing some other study in the annex on long-term effect on air cleaners. Next. So here you see one air cleaner, two about acceptability. When it's empty, the space, the orange is when the air cleaner is on, and the gray when it's not. And on the left is the empty room. It has an improved acceptability. When people emission, there's not much different, but it doesn't really get significantly worse. And if the building materials as a source on the right-hand side, you see it has a significant improvement of the acceptability. So this is one we would continue on stage 2. Next. So here's another one, air cleaner number 4, acceptability. With the empty room, it seems to get worse. Where people are the emission, it's also from the left to the right, the blue one, it getting worse. The acceptability is lower. For building materials, it does improve the acceptability. But this is a case where the effect on people's perception is significant and it is reduced. We will not do a second stage test. Next. So here we are now trying to determine the clean air delivery rate. We have a fixed temperature, humidity, and we do testing at different ventilation rates. Here 3 or 4 different rates for this room. And we have the sensory evaluation both with and without the air cleaner. We also took a lot of chemical measurements. I'm not dealing with those today. Try to better understand what's going on. Next. And here you then see a case again with an air cleaner where when we look at building materials, it has some effect, but not really much. And with people, it just make it worse. Well, next. So the other, I'm missing one slide, sorry. So we have another one, or we have 2 other, where we have seen, like the graphic here, that there is a positive effect on the perceived air quality. So we can estimate, if you take the upper line, that is when there's no air cleaner, tested at different ventilation rate. Here, ventilation rate per person. In that room, we had 3 people, so it's a ventilation rate per person. And the lower, the red one, is then where we have the air cleaner on. And the difference between those 2 is the clean air delivery rate. Now, you can see you can find different rates depending on where you are on the percentage dissatisfied scale. Normally, we try to design around 20%. So if we take the 20%, we get a clean air delivery rate here about 5 to 6 liters per second per person. So from these 2 curves, we can establish the clean air delivery rate. And then we could basically either improve the air quality by using the air cleaner, or we could reduce the amount of ventilation air, and that may have some energy benefits. Because if we reduce the required ventilation, we may use less fan energy, but we also may use less energy for heating, cooling of the outside air. And then, of course, we are also using some energy for the air cleaner. So we looked next on the energy, and here we are looking at an indicator for comparing the efficiency of the general air handling unit for heating, cooling, ventilation, and a standalone air cleaner. Because if you can provide the same additional ventilation with the normal system and not increase energy, so the energy impact of the air cleaner is not worthwhile looking at. So we want to see the effect on the clean air delivery rate in relation to how much energy in kilowatt hours is used. And you can do that on a yearly basis. So if you take the next. So here's then, that's a simulation study. When the clean air delivery rate, which is about 9 liters per second, was measured with the test method I showed you earlier. But then we have done a building simulation rate for a building simulation for a building in Copenhagen. So it's mainly heating, and looked at what is the clean air efficiency per kilowatt hours. So the higher number, the better, the higher is the efficiency, the more you get out of each kilowatt hours related to clean air. And when you now look at the far left, it's a very low polluted building with a heat exchanger. Hex means it has a heat exchanger. And the higher the curve, the better. If we now look at the air cleaner, that's DPAC, gas phase air cleaner, you have a solid line here, orange, and you have a broken line. And that's depending on how high or how low level the air cleaner is running at. But you see, in any case, when you have a heat exchanger, the air quality or the clean air efficiency is higher for the air handling unit. So if you just want to dilute and remove pollutants, it's really better just to increase the amount of outside air with the air cleaner. So we are continue looking at that. Next, it's a next one. I'll just take the last slide. We're trying to look at that, and especially we have, because in IEA annex we have to look at the energy use also. But even if you could not reduce the amount of outside air and have an energy important effect, it may still be important to have an air cleaner because it may remove special substances. It could also be in location. If you go into a school, there may not be an air handling unit, or you may not be able to increase the amount of air for the air handling unit. In this case, it could also be an air cleaner. So the concept was for substituting gas phase air cleaning instead of ventilation. We have set that up. The issue is to find the clean air delivery rate. We have a proposed testing method. Parallel, we're working with standardization on that. We have to be aware, if you want to use an air cleaner for providing some of the clean air delivery, then the CO2 criteria you're using, for example, for demand control will be different, because you can now have a higher CO2 level for the control. So if you have basically an air handling unit ventilation system with a heat recovery, then in most cases for the energy side, it would be better to increase the ventilation through the air handling unit. Thank you.
Thank you, Professor Olesen. Thank you, Bjarne. Very interesting and really interesting study. We are looking forward to future results. But one question related to the kind of metrics you used, perceived air quality. Is it possible to convert and use instead of perceived air quality some chemical concentrations in the air? How do they correlate?
What it shows for most building, it shows. So, for example, in the standards, we also have a method where you just look at mass balance for different substances you have in the air and compare, for example, with WHO guideline for health effect. In most cases, the requirement for perceived air quality would be require higher ventilation, and it will take care of individual substances. Now, for perceived air quality, you are often using a CO2 as a tracer, not because CO2 in itself is a pollutant only at very high concentration. So you use this as a tracer because people, they emit CO2 when they are in the space. But if you look at air cleaner, it doesn't react on CO2. So what we are doing is we are taking, in the test we have done, we have taken several chemical measurements, aldehydes and others, to see if there's something we can relate to the perceived air quality. But I think we need to have more testing before we can come up with a substitute chemical. The other thing, we also need the emission of bioeffluents. So can we come up with a cocktail that simulate bioeffluents? That has been tried for a year, but we haven't got anything yet. But the goal would be that we have a gas or a mix of gas we can use as simulating the source, and we then measure some objectively some components. But I think we are 5-10 years before we have that.
Still, a last question. Can we expect to see something like this in the revised European ventilation and indoor air quality standard?
Yeah, we already have introduced the possibility. The problem is that we cannot refer to a testing standard, how to test it and how to determine the clean air delivery rate. But I think we will work on it so it is ready also when a testing standard is available. So the standard itself is ready to take that into account. But it requires a test.
Okay. We are looking forward to that. Thank you, Bjarne. Thank you very much. Very interesting. We'll go further in the program, and next speaker is Professor Jarek Kornetsky, who is also the chair of the RIVA Technical Committee and working as a professor both in Estonia and Finland. And he's talking about ventilation, air cleaning, and airborne transmissions. Please, Jarek.
Well, thank you. So I will start with a very short background. When we speak about viruses, when it is important to control the virus concentration in the room, and these removal mechanisms which are possible are ventilation, when filtration already being spoken in different presentations, but in this case we speak about the particle filtration, especially when disinfection with UV would be possible, and when we have these natural removal mechanism like deposition of the particles and inactivation, so that is say of a virus. And in the case of a low ventilation rate, when and no air cleaning, virus concentration in the room will be high. And when we are basically calculating what is the dose, what is the exposure, so this is a product of the breathing rate we cannot change, and multiplied by concentration and by the time. So the concentration is basically only thing we can change by these measures in normal indoor spaces. And in the case of a high ventilation rate, yes, concentration is much lower, and then the exposure is much less. And it is also shown with short range or close proximity and long range transmission difference. Concentration can be very high close to the source, and when it will decrease to the level what it will be in the well mixed air in the room, that can be taken as a constant in the most cases. So typical guidelines between 1 meter and 2 meter to keep this physical distance, when we can speak already about the background constant concentration in the room. When it is important to understand that these viruses are not naked, but they are contained inside these exhaled respiratory fluid droplets. And these have a distribution starting from less than 0.5 micrometers, and our interest range is perhaps up to 10 micrometer, because larger droplets will settle down very, very quickly. And what will happen with these fluid droplets, which people normally exhale? So there is evaporation and desiccation process, what is actually very fast. And when evaporating, these droplets will shrink roughly to 1/3 of initial diameter. And after this evaporation process, the end product is basically, this is a solid particle. This is not anymore a liquid particle, but a solid particle. And for that purpose, this mechanical filtration with particle filters is very, very effective. And the process is very fast. So for instance, for 10 micrometer fluid droplet, it takes only 0.1 second to desiccate and to be this small shrinked particle. So this is a physics behind these transmission what we have indoor spaces, and there are already quite many studies available, experimental studies, and also one epidemical study from Italy, where they were able to show that well-ventilated school buildings, where the ventilation was 10 liters per second per person or higher, this reduced the likelihood of infection for students by 80%, compared with the classrooms with natural ventilation, and this natural ventilation was in these cases very, very low ventilation rate. So this is a tremendous effect of well-ventilated rooms can be seen from this quite an extensive study. There are also some experimental studies with air cleaners, and they have tested many positions of air cleaners in the classrooms, different setups, but all studies have concluded that central locations would be important, so not place your air cleaner to the corner where the impact will be less, but use central locations. And it is recommended that at least 2 air cleaners would be needed per classroom, and very high air change rate of about 5 air changes per hour through the air cleaner. So this actually equals to ventilation rate in well-ventilated classroom. It's also 5 air changes per hour. And when we add air cleaners, when we double this removal rate to 10 air changes per hour, and indeed this would result in very effective virus removal. It is important to understand that these air cleaners will not replace outdoor air ventilation, but support it. There is no impact on the CO2, for instance, but air cleaners are very effective on the solid particle removal, so viruses will be effectively removed. And there are also some Finnish studies available showing from laboratory experiments and CFD simulations that 50% of a reduction with air cleaners in offices is possible. Then there are also studies available about targeted and personal ventilation solutions, and it has been partitions being studied and different air distribution methods. And some sort of a summary is that the ventilation effectiveness can be considerably improved. It has been in between 1.4 to 10, factor 10 in these studies, meaning that you can reduce the ventilation rate if the ventilation air distribution and the ventilation effectiveness is good. But still practical applications are quite limited, and I think many studies are still in the process. So this COVID provided a good new reason to start to study this type of occupant targeted ventilation solutions and how to get the clean air more directly to the breathing zone and to improve ventilation effectiveness in this way. A lot of guidance has been created, many scientific publications, for instance, including REFA guidance and WHO ventilation roadmap and so on. But currently, yes, this infection risk-based ventilation design is not yet addressed in the standards or in the design guides, and this has been the reason why Nordic Ventilation Group and REFA have been working to propose a method to calculate infection risk-based ventilation rates and are proposing to include this in existing ventilation sizing design methods. So basically the method is quite simple. It includes only 4 steps: how to calculate the target ventilation rates, when to apply ventilation effectiveness to adjust these ventilation rates to actual air distribution used, when compare with existing perceived air quality ventilation rate, what is in the existing standard and is widely used in many countries, and when to select the highest of these 2 as a design ventilation rate. Before I will go to this infection risk-based ventilation rate, I show this existing one, what is in the standard EN 16798 part 1. Bjarne also showed in the previous presentation the same equation, what is based on the people component, how many liters per second per person ventilation needed, and per floor area component, so how much ventilation needed to remove emissions from the building materials. And for instance, in the category 2, one will end up with this equation, but 7 liters per second per person plus 0.7 liters per second per floor area is needed in category 2, and this will result, for instance, in classrooms about 5 air changes per hour. And the new method provides something similar what comes to the target ventilation rate equation. This is also based on the number of persons on the room. So it is assumed that 1 is infector, so this is the reason for n minus 1, and the second term operates with the room volume, and this term represents deposition and the removal mechanism of viruses. And depending on the activities, we expect to have in common space categories, ventilation airflow rates are different. So this is the difference compared to the common sizing of a ventilation where activities are considered to be the same. But in this case, it will make a difference if somebody is speaking or making a physical activity when more ventilation would be needed. And this is a target ventilation rate what will apply in the case of a fully mixed air distribution. And in the case of a real air distribution system, we need to adjust this by the ventilation effectiveness, which is also known as a contaminant removal effectiveness. It is possible to include air cleaners to this equation when we will get removal term a bit longer, where the removal rate by filtration is included. And the application of this equation will provide results what are calculated in typical rooms in this table. For instance, taking a classroom, 56.5 square meter, 25 persons, quite a common classroom, when we will see that the ventilation rate about 3.9 liter per second per square meter, about 9 liter per second per person would be needed, very close to 5 air changes per hour. And this is slightly less than the category 1 perceived air quality ventilation rate from the existing standard, which will provide 5.4 liter per second per square meter. So basically in these highlighted cases, existing standard provides higher ventilation rates compared to those calculated based on the infection risk. But these other values, yes, when this infection risk-based ventilation rate is higher. But what we see that in the classrooms and in offices, in common office spaces, category 1 ventilation rate is in most cases enough to satisfy also this infection risk-based ventilation rate. And another way how to use this equation is if we already know the ventilation rate, then we can calculate how many persons can be in the room in epidemic conditions. So it also indicates that reduction of occupancy is efficient measure in the epidemic conditions. And in some cases, this reduced occupancy is highly useful and well justified. For instance, in the meeting rooms, every second seat should be empty to keep this 1.5 meter distance, and this will automatically lead to about 50% of occupancy reduction, and when ventilation rates would be reasonable also in the meeting rooms. Finally, I would like to say a couple of words about ventilation effectiveness and how these can be measured and which values are available or are not available. So when we speak about virus risk control, when we have our assumption is that there is one infector in the room, so it is a point source. And existing values of the ventilation effectiveness apply for normal occupancy, so it's basically a full occupancy in the room, all persons emitting odors and CO2, and this will correspond to distributed source. So there is a difference of a point source and distributed source, and this is the reason why existing ventilation effectiveness values cannot be used to calculate this infection risk-based ventilation rate. So basically, equation is very simple. It can be calculated as a tracer gas concentration in the extract air divided by breathing zone concentration, and tracer gas measurements or CFD simulation can be used to determine these values. This is one example showing a large teaching space about 130 square meters. We can see that there are 5 supply air diffusers on the ceiling, and in this case emission source is located in that end of a room, and when the concentrations are higher close to the emission source, and on the right figure, emission source is located in the middle of the room, and still concentration distribution is very different in the room. So this local air quality index indicates the air quality, the higher the value, the lower the concentration, and these white regions show the zones with the lowest concentration. It is mixing ventilation solution, but we can see that in the case of a point source, mixing ventilation is not working as a mixing ventilation, and there are a lot of concentration differences. This is another example, just a meeting room with active chill beams, very common mixing ventilation air distribution once again, but not working as a mixing ventilation for the point source. And here we see on the top figure, if source is far from the exhaust, then the concentration is so that near the source the higher concentration, and then it will slowly decrease towards these extract air devices. And in the bottom figure, the source is close to the extract air devices, and then the concentrations are much lower in the room. So this illustrates the problematic why we need to measure or determine these ventilation effectiveness values in the case of a point source, and there is also good potential to increase these values. It is not only the ventilation rate what is important, but it is also important how ventilation systems are operated. So many ventilation systems are demand controlled, and in epidemic conditions we need to overrule this operation so that CO2 set point can be changed, and it is recommended to use 550 ppm set point when the ventilation should operate at the full speed, roughly all occupied hours, as shown is in this figure, where you can see that the ventilation is kept in minimum out of occupancy, operated couple of times in the night time, and then started 1 hour before occupancy will start, and then will operate at full speed, 4 liters per second per square meter. And you can see 5 days. This is 1 week, and when it is a weekend operation, no occupancy in the rooms, and it will be different compared to the common demand controlled operation using a set points perhaps 800 ppm in the classrooms. But in the epidemic periods, these set points have been to be replaced to 550 ppm, and then we can be sure that the ventilation systems will operate at full speed, what is needed for the effective removal of the viruses. So this method is proposed to be implemented in the ongoing revision of this standard, and when it is proposed in the format of a generic equation, very similar to existing perceived air quality equation, also having 2 virus-specific parameters, and then the number of occupants and the room volume in this equation. And these virus-specific parameters can be defined as a part of a national annex. So basically every country can decide which values and which risk levels would be relevant to be applied. And this provides an opportunity to operate with very generic equations and to show these mechanisms. What is important? It is important how many persons will occupy the room, and when the room volume will play also an important role. And then it needs to be described how the ventilation effectiveness can be measured and calculated. So a short description for these purposes. So maybe yes, this ventilation effectiveness is something what will need more attention, because advanced air distribution solutions can enable to reduce the ventilation rates This slide shows an example how a tracer gas measurement can be conducted in the laboratory to measure a couple of setups of classroom ventilations and to determine these ventilation effectiveness values. So this is one setup of actually modeling the ventilation solution what has been used in the renovation of school buildings. It's not a perfect ventilation solution, but shows how the air movement will happen in the classroom and how this displacement type of airflow pattern can be achieved. Actually, in this case, it also generates quite a lot of draft, but this video is has much more high velocity than it is in reality. So, and for instance, in these 3 cases studied in the laboratory, we can see that the ventilation effectiveness values are quite different. So in between 0.77 to 1.36, so almost by factor 2 difference, and this factor 2 difference will mean that in one case you will need 2 times higher ventilation rate for the same risk level. So to conclude, there is already a lot of evidence available, and infection risk-based ventilation design method has been proposed to complement the existing standard based on the perceived air quality. And the idea is that the highest ventilation rate given by these 2 methods shall be used. And it is important to understand that operating with these risk levels described in the method, the aim is not to eliminate, but just considerably to reduce the infection risk and to know what is infection risk in these common indoor spaces. So it provides an opportunity to design all the spaces for the same indoor risk level, and this is something different from the healthcare setting when the infection risk must be much lower. But in this case, these ventilation rates would be reasonable. In typical classroom and offices, they are close to the category 1 ventilation rates, and for instance in classrooms ranging in between 8 to 13 liters per second per person in different cases. The method also indicates that in highly occupied rooms like meeting rooms or gyms, when infection risk-based ventilation rates can be very high, but they indicate that reduction of occupancy would be feasible instead of doubling the ventilation rates, and indeed also hand in hand with reducing the occupancy is the use of advanced air distribution solutions helping to use smaller ventilation rates. Thank you.
Thank you, Jarek, for the great presentation. I have a couple of kind of clarifying questions. I understand that this model for ventilation is based on research on COVID virus. Can it be applied as well to other type of infectious diseases? And the other one is this ventilation effectiveness. It looks very complicated. Can you see that we will have enough information to have the numeric values in the future standards? How soon?
Yes, so the first question, yes, these ventilation equations were calibrated to COVID, actually to Omicron virus variant, but the same equation with different parameters, just the values will change, will apply also for all other airborne transmission of viruses like a common flu or influenza. So the equation basically is generic, and every year we have these respiratory viruses active in some periods, and when this ventilation sizing method would be valid. What applies to the ventilation effectiveness values? yes, these are to be measured, and I think this infector as a point source, this also is a kind of a paradigm change in the ventilation air distribution design, so that the air distribution solutions can be designed so that they are effective both in the case of distributed sources and in the case of point source. And indeed, there is a measurement effort is needed to conduct these tracer gas measurements, but in these days also CFD simulations are very effective, and many predictions can be done based on the CFD simulations. It would be good still to conduct the measurements either in the laboratory or in the case of a very large spaces when the field measurements are basically the only option. This is something where, let's say, information is not yet available, but I expect that this availability of ventilation effectiveness values will develop, and we will get more data in coming years, because many active research projects are ongoing to study this item.
Okay, thank you. We are looking forward to receiving that information and using that in practice. Thank you, Jarek, very much. This is very nice presentation again from you. Thank you. And thank you all speakers. I think we had an excellent overview of the topic, can air cleaning replace ventilation? Maybe not yet, but some of it, and maybe in the future we know more and can replace and use most energy efficient methods to keep up the good indoor air quality. But please remember that these presentations and recording is available on Scanvac website later this week, and knowing Siru's working capacity and speed, I think I will predict that they are tomorrow already on the website. And thank you, Siru and others, for organizing this webinar. I think this was excellent, and I believe that the Nordic authorities will continue this tradition also coming years. But finally, I like to remind that this topic will be discussed further in the Room Vents conference, which will be in April in Stockholm. And I hope many of you can attend this conference, and we will continue discussion in this topic. Thank you, and we'll finish here.